Okay, welcome to Science for the Board. Tonight we're going to hear from Ed Friedman. Ed graduated from the University of Maryland with a BS in physics and Wayne State University, PhD in physics. His 48-year career focused on the application of lasers and optics in astrophysics and monitoring of climate and environment. In addition to his work in the aerospace industry, he has been a consultant to NASA and the National Academy of Sciences. He was adjunct professor in the aerospace department of the University of Colorado, instructor in graduate orbital design at Webster University, and has taught math and astronomy at community college level. He is the author of 4 books on optical engineering and 1 book on orbital dynamics, 1 book on energy storage technology. He holds 1 patent on space lasers and is author or co-author of 79 professional journal articles and related publications. He's currently an adult education instructor in cosmology at Colorado State University and occasionally on cruise ships. He's a volunteer lecturer in advanced topics in physics and mathematics at local high school. In his spare time, he's a piano student and fee-free math tutor. He and his wife reside in Colorado with their daughter and her family and include their 6-year-old grandson. They have a total of 6 grandchildren. Ed?
Yeah, so let me introduce Scott Acton. I met Scott in the year 2000, actually, in Hawaii, when he was running what I'll call a boutique advanced technology optical engineering company. And he hosted a workshop on what he's going to talk about tonight, wavefront control, and was at the time doing most of his work, I think, for Keck, the Keck telescopes on Hawaii at the time. But he's got a vast array of experience. I've recently read his PhD thesis from Texas Tech, and you can see he's an expert on dealing with the adverse influence of the atmosphere on ground-based telescopes. He's worked on the Giant Magellan telescope, and he's a central player in any success that comes from the James Webb Space Telescope. You could point right at Scott because he's involved and leads the engineering effort to understand how to manage the wavefront control on that very complex observatory. So we can get into the technical part. Let me turn this over to Scott. We're very lucky to have him talking to us. So Scott, you're going to want to pull up your slides, and Bruce is going to let you share your screen or the appropriate app. And let's light this candle.
All right. Am I currently sharing my screen?
Yes, yes. And switch to presentation mode, I think, and we will.
Okay.
We'll have what we need. There we go. Fantastic. All right, take it away, Scott.
Okay, let's go back. Ed, very kind words. Thank you very much. You know, it's been quite a opportunity to be able to work on this telescope. So I'm going to give a talk that I've given several ones since we finished lining the telescope, and this has kind of evolved into a combination of lining the telescope and also a little bit of bicycling, which Ed asked me to throw in here. But I'm going to show a lot of pictures that come from the Webb telescope. But most of my pictures are not going to look like this. My pictures are going to look like this. Okay, because they got to look like this before they can look like this. And so what I'm going to do is tell the story of how we started with this randomly deployed telescope in space and ended up positioning all the mirrors and the optics so that it produces a diffraction limited image across the entire science field. Here's the telescope. Oh, I should back up just a little bit. I'm also going to tell another story, and that's the story of how I used this opportunity, the delays in the completion of this telescope, to fulfill or attempt to fulfill anyway a lifelong dream, and that was to ride my bicycle around the world. But we'll get to that in a second. Here's a picture of the telescope, or a drawing of the telescope rather. There are no pictures of it, not in space, because ambient light never gets to this side of it, for one thing. But I thought I'd better show you at least one picture of the mirror. And here it is. I just happen to be standing at its center of curvature near there when we snapped this picture. If anybody ever wants you to give them a good definition of narcissism, this is it. The narcissism is looking at your picture, your reflection in a $10 billion mirror. And that's what I'm doing in this picture here. But here's a good comparison between this and the Hubble telescope. Some stats there on the right. But most importantly, each of these segments has a name and a number. I mean, we know them like we know our children almost. They all have their different characteristics and issues. Here's a picture of a scale model of the telescope out in front of it's an old Catholic church in Dublin, Ireland. That was been converted into a museum. And here is a picture of basically the back of one of these mirror segments. Now, each of these segments is a mechanical device. It basically is, has 6 actuators to move it in rigid body control, and then a 7th actuator to bend the mirror, to change the radius of curvature. And all this, everything you see there for the most part is made out of beryllium, which is a very, very light material. And just here, a real quick overview of the science instruments. Now, one of the reasons this telescope is so expensive is it has 9 different science modes, whereas most spacecraft just have 1. And this has multiple science instruments that they share the field. In theory, you can expose them all at the same time, although in general, that's not done. But each one, this is the near-infrared spectrograph. Here's the near-infrared cameras. Those are basic imagers. This is the mid-infrared imager instrument. This is the Canadian instrument, the near-infrared imager and slitless spectrograph, or NIRIS. And these are the fine guidance sensors, which we use to control the pointing of the telescope. All right. Now, most of the stuff I'm going to show in this presentation came from the NIRCams, and most of that came from this single detector right here. But even so, that single detector is 2048 by 2048 pixels that are sensitive in the infrared. Now, just a little bit about this bike ride. This was an interesting opportunity. It was a time in my life when I kind of didn't matter to the project, at least not for a year or so. My kids were grown and had left the house. I could sort of afford to take a year off, by and large. And although I was about 55 years old, my body hadn't really figured it out yet. So I decided to take a year off and try to do a round the world bicycle ride. And when you do these, I've done a lot of bicycle touring before. And when you go to various places, you're always sort of a little celebrity when you go into town. And people ask you the same questions. They say, where did you start out? Where are you going? How many miles in a day do you ride? And then the fourth one, why are you doing this? That fourth question is a hard one to answer. And a long story short, either you understand, you get the concept of a long journey by bicycle, or you don't, and you never will. And that's not a bad thing. It's just different people have different emotional responses to this. So what do? We associate it with something that people can understand. Well, world peace was already taken. So I decided to form the James Webb Space Telescope World Bicycle Tour. The mission is to ride the bike around the world, or nearly so, and give a couple of lectures every week to communities, schools, colleges, and that sort of thing. So we got, I got a website, this logo here. The website's still there if you want to check it out. We got these bicycle jerseys. I got people to go with me on the ride. I got sponsors, and it's all set to go. And I also got one other thing I hadn't counted on. I got a little pain in the center of my chest every time I would get on the bicycle and ride. Now, I was bicycling 200 miles a week at the time, which is about as far as you can go and still have a full-time job. And everyone told me it couldn't possibly be my heart because I was just in too good a physical condition. That's the truth. But one doctor led to another, and one test led to another. And come to find out, the arteries in my heart were clogged beyond anyone's wildest imagination. I had days to live and didn't know it. My daughter was getting married in 3 days. I asked the doctor if we could wait until after the wedding to do the surgery, the bypass operation, and he said, yes, of course. That way all of my family would be in town for the funeral. And so we didn't, a surgery it was. I never got off the table, went straight to Loveland and had this done, and attended the wedding by FaceTime. But I always show this. I've given a lot of talks since we commissioned the telescope, and I talked to a lot of young people. And I just want to say that I'm not 100% certain, who's in the meeting today, but so in a general sense, if not for your benefit, for all the young people that are going to see this, I want you to know that the science behind your blood chemistry and your risk for heart disease is 100%. You can get a blood test that will tell you your future. I know that in a large audience, whenever you give a talk, a significant fraction of those people will have to have heart surgery at some point, but I try to tell them that this is optional. You really don't have to do it. And all you have to do is just, everybody is intelligent. You can go out and get yourself tested and change your lifestyle, take medication, whatever it takes to avoid this. Because although I was in good shape and I did really, really well, it's the most horrible thing I've ever experienced in my life. And so that's kind of my mission now, is to talk people out of having to have this surgery. In any case, let's go back to the commissioning the telescope. Now, this is the layout of the wavefront sensing and control room, where my team and I hung out for about 5 or 6 months. And you can see there's a couple of our guys. That's Bob Brown on the left and Larkin Carey on the right. And they're doing, looks like a course phasing operation at the time. But I also want to talk about a couple of enabling technologies. And one of them is known as phase retrieval. Now, a lot of what we did in the commissioning of the telescope involved this technique called phase retrieval, which to me is nothing short of magic. And here's the basic idea. Let's suppose you've got yourself a complex function, has a real part and an imaginary part. I can make some very, very simple and reasonable assumptions about that function. If I can assume that I can put a box around it, so it goes to 0 outside of something, or at least falls off fast enough so that it effectively goes to 0, and that it's analytic, it doesn't have any discontinuities in its function or in any of its derivatives. If that's the case, those two very simple assumptions, if I know the real part, I can find the imaginary part, or likewise, if I know the imaginary, I can find the real part, and therefore the entire function. It's not much of a stretch to then say that if you know that's the case, you can use this to find, if you know the magnitude, you can find the phase. And that is what we're doing here. We are measuring the amplitude of the electric field in the image plane or near the image plane. And we know sort of the amplitude of the electric field in the pupil plane of the telescope, because that's basically just the geometry of the pupil. So using that information, we're able to determine what the phase is. Well, the phase of that electric field tells you what is wrong with the telescope, what you have to do in order to realign it and fix it. Now, there's a catch, however. Just because you know a solution exists does not give you that solution. Okay, and this is what we spent many years or decades actually learning how to do, computer algorithms and analysis to turn those measured amplitudes into phases. But we use phase retrieval throughout this process. And everywhere I show here in the blue, we use it, we create a defocused image by moving the secondary mirror of the telescope. But in places here, like in the green, instead of defocusing the entire telescope, we just put in a defocusing element that's in the main science instrument, and it enables us to take a defocused image without having to change the focus of the whole telescope. And that's important because you never know, when you move that secondary mirror, it might be the last time you move it. And so you don't want to have to take it out of focus unnecessarily. There's other things that are done besides phase retrieval. We do a lot of centroid analysis for one thing or another. And there's also something known as dispersed fringe sensing that we use to determine and therefore correct the piston errors between adjacent segments. All right. So now, as you all probably saw the animations and everything, this telescope deployed, and it was quite a nervous time for everybody, but it seemed to work really, really well. And Northrop Grumman just hit it out of the park. They did a phenomenal job on these mechanisms, and everything deployed the way it was supposed to. But then we came to our job, which was deploying the mirrors. Now, the mirrors sit on top of these actuators, and they have to be down to basically at their 0 position for launch so that they can survive all the vibration. But once we get it into space, we began the process of moving them about a ½ inch, nanometers at a time. This was a very conservative process. We'd go one step on each motor and then one revolution, and then like a millimeter at a time, just one actuator after another. And it took a long time to do this, took about a week or so. And someone pointed out that the mirrors are actually deploying slower than grass grows. I mean, grass grows faster than these mirrors deploy. And Jane Rigby, the project scientist, went off and made us a chia web, which was, a little like a chia pet, but she put seeds on it. And we watered the web, this chia plant, and sure enough, it grew faster than the mirrors deployed. And this became, the little grass growing became the icon that people could see on their computer consoles for a while that determined the status of the mirror deployment. But eventually everything got deployed. So then back to this bike ride. So I left Boulder, Colorado on April 1st, heading north. Now I had to change all my plans because I had to have this heart surgery, but eventually I recovered and got on the bike. And I went north on April 1st, 2016. I got snow there on the road, so it was I got very, very lucky with regards to the weather. And then went north up through Colorado and Wyoming, across the Continental Divide there in Wyoming. All kinds of winds, terrible winds, terrible fifth graders even. This was one of the first talks I gave. Man, what an intimidating audience. There was probably 200 or 300 grade school kids, and every one of them wanted a piece of me in one way or another. And just, I barely got out of there. But it was really neat to see all the enthusiasm. Kept going up through Wyoming, Thermopolis, Wyoming, the world's largest mineral hot springs, up into Graybull. They welcomed me to give a talk there with a cake. Into Montana. This is Bozeman Pass. I about bought it on Bozeman Pass. Boy, that was scary. But eventually the storms passed and the skies cleared. And it was really, really beautiful. And it was began to be a nice, pleasant ride. So we began the first flight in the telescope by pointing the telescope to a place where we knew there would be lots and lots of stars. So we pointed at the middle of the Large Magellanic Cloud, just hoping we could see something. Now the idea was we would point this, get a cloud of thousands of stars into the telescope and try to just see what we can see. And so here's the very first image we took. This is just me snapping this photo with my cell phone, but everybody was really, really happy because we saw something, and the science camera was alive. We were able to get images. There wasn't a piece of mylar in front of the entrance aperture, for example. Everything was working. Now, what we're really seeing there is all the stars, all the segments are looking at a slightly different part of the sky. So you see a complete image of the sky for each of the segments. So you really see, roughly 18 copies of the sky there, even though we're looking at just a tiny, tiny part of it. And then all the aberrations are in that, those segments are visible there as well. And although people were really, really pleased to see this, I was quite nervous because some of those images are way more astigmatic than we were expecting, and they're way out of focus as well. So something was going on. We would not resolve this problem until Super Bowl Saturday. This was on February 2nd, and it was a couple of weeks before we were able to go away and realize that everything was fine. We were afraid we had seriously damaged a couple of the segments as it left the Earth due to overheating. But once we knew we could get light on the detector, we pointed the telescope to the kind of like the opposite place in the sky. We pointed it to a bright, isolated star and formed this little raster pattern just by pointing the telescope around and taking images on all 8 of the NIRCam detectors and then stitching them together. And we were very pleasantly surprised. It turns out that the segments images from each of the segments were not spread out as much as we were anticipating. And the pointing errors, the bore sight error of the telescope was quite a bit smaller than we were expecting as well. Now, the downside was, however, we were having a hard time pointing the telescope. So even after we calibrated it, we would tell it to go one place, and we were expecting it to be able to do that to within, say, 1 or 2 arc seconds. In fact, it was closer to like 30 arc seconds. So we had to learn to live with that uncertainty. Here is the mosaic. And if you counted all those images there, you would see 18 of them. So the idea is we need to figure out which one is which, and we'll do that in a second here. But here is the answer. Each of those numbers correspond to the number of the segment that produced that. And we had a couple of ways that we figured that out. By the way, these are the wings. So these are the sides of the mirrors that deployed out, they're like a drop leaf table. And as you can imagine, they sort of stick together when they deploy because there's a whole separate deployment mechanism. But now we're going into Canada back to the bike ride. So I rode across the Canadian border. It's amazing how far you can go at 50 miles a day. I finally gave up on Google Maps because it was taking me onto dirt roads, but Alberta and British Columbia, the Yukon, eventually Alaska. What a beautiful, beautiful place. Just unbelievable. Just imagine that you're out in Colorado for an afternoon drive. You're taking a drive up on a Sunday afternoon, maybe, just to appreciate the mountains. And just imagine that drive continuing for 2,500 miles. That is what the Yukon represents. It seems to go on forever. And I have to tell you, it was just so incredibly beautiful, just very, very peaceful, but very, very unforgiving as well. You're on civilization there on the road, but you go 50 feet either direction and there's nothing as far as you can imagine. But what beautiful rivers. Every river was just loaded with fish, just fantastic. On into the Yukon territory. I really, really love that place and I hope to go back someday. It's nice to bike through a place that is bigger than yourself. And I really, really enjoy that. Such beautiful scenery. There were times I met the head of the Canadian Astronomical Society. I love this place, except for the bugs. The flies got to be a little unbearable, but I got out of there before the mosquitoes got unbearable. So I came to a fork in the road and I took it and eventually ended up in Alaska and rode all the way to Fairbanks. And at that point, I ran out of road and decided to go to the next phase of the ride. So back to the telescope. We could tell from those images that there was a nominal focus bias. We needed to move the secondary mirror in focus before continuing a little bit. So we pointed the telescope somewhere where we were guaranteed to get at least a handful of those segment images. And we stepped the secondary through its focus. Now, we were plagued by the inability to hold the telescope stable while we were doing this. So I was not able to use the spot motion of an individual segment as a mechanism for determining which segment it was. However, in doing phase retrieval now on one of those groups of segments, I found that the algorithm was wanting to draw both into the phase and the amplitude this vertical line across that. And that had to be because that was one of the images, one of the segments with the secondary mirror support structure going through it. In this case, it was segment 12. Well, since I knew how segment 12 was supposed to move as we went through focus, I was able to shift all these groups of 8 images accordingly to make it look exactly like that. And then based on the simulations, which are in the upper right, it then allowed me to determine what all the other segments were. So I was able to get all this just from that one shadow that was in the phase retrieval result. So now we've identified a lot of the segments, but some of them had to be identified just simply by pointing the telescope to a spot in the sky and wiggling that mirror, taking images before and after. But eventually we knew what all segments, which one was at each spot, which segment is associated with each spot. And we decided we would base the bore side of the telescope or the center of the optical axis on the geometrical average of the segments associated with the central backplane, so the center 12, and not allow the wings, because who knows how they're going to deploy, bias the result. Well, the geometrical middle of that is where the crosshairs is, and the idea is that we need to tilt all those segments such that they land in a tight little array near that crosshair, and we will move the telescope so that the center of our favorite detector gets to that point. Now, this was something because of the pointing errors we had. We were not able to rely on our software, so this all had to be done by hand. Literally, I did it from the IDL command line and just copy and paste and sent these commands turned into moves to the telescope. I was quite nervous about it, but at the end, it all worked out. And here's what happened when we took images before and after each move. And eventually all 18 segments showed up on this one detector. Now, it should be in the middle, but those were the pointing errors. And they should have been in a tight little circle. But 5 days had gone by since we took that initial mosaic image. And this is stretched out now, representing the basic, the thermal distortion of the backplane due to the cooling of the telescope. but no matter, we just measure the positions, and it's possible then to tilt these things into a nice determined area. And there it is. We have 18 segments in an array. We colored it blue and released it to the public, and it went viral. So then I continued with the bike ride back to there and started to go to Europe. And the cheapest place to fly at the time, I was worried about money, was Gibraltar. So I went to Gibraltar, but unfortunately on a very questionable airline, and they would not give me my bicycle. I even attempted to bribe various officials, but it was stuck in Morocco, and they wouldn't get it. And it took a week to convince them to send it to London. And so I was able to get British Airways to send me my bicycle for free. But Gibraltar was a very interesting place. But Spain was a very, very difficult place. Spain just about killed me. It was so hot, and the roads that bicycles were allowed on were quite difficult to navigate. But it got better. France was beautiful, wonderful, boy, along the Loire River, and such friendly people. I don't know where the stereotype ever came that the French are not nice to Americans. I just didn't encounter any of that ever, not even once. Just wonderful places, beautiful structures and history, and just the castles. And then on to Switzerland. Switzerland is interesting. I was on an international bike path, which is shown in the on the left side of the page there. A little goat path. Well, that is Eurovelo 6. That is an international bike path, and at the end of that little trail is a bridge, and on the other side of that bridge are stairs. Of course, you have an international bike path. Of course, you have stairs in the middle of it. But nonetheless, took my bike apart and was able to get it up the stairs and on, and then went to the Geneva Observatory, where I was giving a talk. And that's really cool, because this observatory is older than the United States. And I arrived there on my bicycle, and it was fun. Claude Nicollier, which a lot of people probably know from Ball Aerospace, showed up to hear me give my talk, and then it was really nice to have him there. And then into Germany. I rode across the length of the Danube River, and what a beautiful, beautiful place. I highly recommend it. If you ever want to do any touring, bicycle touring in Europe, I highly recommend you bike along the Danube River. It's something you can do, and there's plenty of fun things to see along the ways, and just beautiful. Into Austria, eventually ended up in Vienna. That was a really interesting place there. And Anton Zeilinger hosted me for a day. You know, he just won the Nobel Prize too, which is pretty cool. Pretty smart guy. And then I didn't even know I was going through Slovakia, but I looked at my route. Hey, I'm going to go to Slovakia. So I booked a tour, a lecture there, and they went to the university, and I gave a talk, and they put me up for a night. And then on into Hungary, and the same kind of thing. Just into Budapest, as a place I'd never been before, but my goodness, what just phenomenal architecture, just beautiful. So back to aligning the telescope. So here we are, we had all these images in this array, and what we're going to do is we're going to use the secondary mirror to defocus all of those images so that we can then make corrections of the position of the secondary mirror, and also corrections to the individual segments themselves. And here's the first set of results. Now at the top, I show the phase, the upper left, and in the bottom is a high-pass filtered version of that. And you can see there's a couple of those segments have like a little donut pattern, like a dark spot in the middle. Now, two of them, the ones behind the secondary mirror support structure, we knew that was the case. Those mirrors were unfortunately polished to the wrong radius of curvature, and we opted to basically leave them there rather than remake those mirrors, because it's not a terrible problem. But the other two in the upper right and left corners, they were not supposed to be like that. So what had happened, somehow there was a bookkeeping problem. We still don't really know what caused it. The radius curvature actuators were set to the wrong value. And no big deal, but it was important that we corrected it with radius of curvature actuation rather than piston. Because if we didn't, it would have driven it outside of the capture range of one of our other processes, and we would have been in a contingency. So that's what we did. We went ahead and corrected those errors and took a couple of iterations. And here's the images before. at the top and afterwards, after performing global alignment. And you can see in the center there that all the images are now crisp and tight, and we can go on to the next steps. And the next step is image stacking. Now, the idea is we need to tilt these things so that they fall on top of each other precisely, but we don't want to use too much of the fine mechanism's dynamic range. Each of the actuators has a coarse mode and a fine mode, and we want to save the fine mode for some of the finer operations. So we have to do this in a multi-step process so that we can guarantee that we get everything stacked with the fine range in the center of its dynamic range. And here's what we ended up with. And so now the segments are all stacked on top of each other, but they're not phased with respect to each other. Okay, so we'll see an image, but it won't be a perfect image. So first of all, what we did was we took a pupil image, and we showed this image, or an image similar to this, to the administrator of NASA. And Administrator Nelson said, "Oh, you mean a selfie?" And we thought, well, yes, of course, that's exactly what this is. It's a selfie. He's a good communicator, and he recognized that that's something the public would identify with. And so this became the selfie. But we also took an image of the Large Magellanic Cloud. And even though the images, the stars are not, the segments are not phased at this point, it still makes a nice image. And I put this on the lock screen of my iPhone. So then after they're stacked, we went on to the process which allows us to measure the piston error between the individual segments. Now, I won't go into detail about how this works, but it uses something known as dispersed fringe sensing. Each of the pairs of the segments that you see there are used to create a spectrum on the detector, and you can analyze that spectrum in order to determine what the piston errors are. It creates something like a barber pole pattern. And the frequency of those, the fringes or the lines in the barber pole pattern tell you what the piston error is in the segment. But if you get too large, we end up losing the ability to sense it. So fortunately, we could see these on some of the longer wavelengths on the other detectors, and we're just barely able to measure all the errors and apply corrections. So we got very, very lucky in that regard. So the corrections were somewhere between basically plus and minus 1/4 millimeter. Those were applied, and we went on to the next step. But before that, I want to go on to the next step of the bike ride. So I came back from Europe after biking across Europe and went back to Boulder, Colorado, and put my bicycle at exactly the same spot out there in front of RA7, and then instead rode south. And I really, really enjoyed this part of the ride. I'd consider this to be kind of what America looks like, you know? Let's see, let's get here. There's a better picture. Something about those kind of scenes just really appealed to me. This was a ride where I actually got out of shape. It was so easy, and there were only a couple of difficult days, and there was all this fattening food to eat the whole way, and I actually gained weight, and I lost conditioning throughout the process. But nonetheless, it was pretty cool. Bed bugs in the hotels I could have done without, but even those can be managed if you pitch your tent. And then on to Texas. There's my good friend Sam Cooke. He's actually a professional opera singer. He was wearing the right bike jersey, so I decided to let him ride with me for a while. There we go, into Texas. Fire ants. I discovered fire ants in Texas. Then I pitched my tent amidst those things and just crossed my fingers and hope they didn't get inside. That was the night that I woke up in the middle of that night, not to fire ants biting me, but to the news that Donald Trump had won the presidential election. That was quite a day. On into Austin, Texas, to give a talk, and somebody made this nice little drawing for me on the whiteboard, the blackboard. Into Louisiana, crossing the mighty Mississippi River. I got to tell you, it's not easy to cross the Mississippi on a bicycle. It's easy for cars, but it's pretty hard for a bike. And then on to the great state of Alabama. That was a pretty cool place. And into Florida. Now, I saw this guy on the side of the road pushing this gigantic ball, which was painted to look like the Earth. And I don't know this for a fact, but I think this is a somewhat famous man named Mark Balmer. He was a poet who decided to walk across the United States barefoot to raise awareness for climate change. And so I suspect that was him. He was in Florida at the time. And unfortunately, just a few days after this, he was struck by a motorist and killed. And that was the end of his walk. But I don't know that was Mark, but I think it was. Anyway, there he is. into places I'd never seen things like this before. I'd seen pictures of them, but they're just phenomenal. And the Florida Keys, oh my goodness, what a place. These causeways just go on forever. Amazing, amazing place. So the next step in the commissioning process is to measure the field-dependent errors. And for that, we use something known as coarse multi-field measurement. Now, here's an equation. It turns out that the field dependence of the alignment of the telescope as a function of where you have incorrectly placed the secondary mirror is something that you can actually calculate. And there's a very simple linear equation, as a function of the 4 degrees of freedom of the secondary mirror and of the basically terms that we refer to as focus and astigmatism. Now, it's a fairly straightforward expression, but I want to point out, particularly to you people, because you have a technical background, everything is easy when you know the answer. And when you don't know the answer, it's not easy. And it took us years and years to determine this relationship. It was something that multiple organizations, Goddard, JPL, and Ball Aerospace worked on for years and did not come up with the answer until we did using an integrated telescope model to try different things. But in any case, with this equation, you can make measurements of how the wavefront changes as a function of field position, and it tells you what to do to the telescope to fix that. So to make these measurements, we came out of coarse phasing and we moved all the little spots to form this tiny little array. Now we keep one out so that we can use the fine guidance sensor to guide on it. Now we're not guiding on that by itself, but there'll be a different star down on the fine guidance sensor. And the software doesn't like to try to guide on stars that are too close to each other, so we have to move one off by itself. But by looking at how each of these patterns, these images changes as we move around the science field, we can determine what the focus and astigmatism terms are and how we can, and therefore correct it by moving the secondary mirror. Now, so we also have to do something else though. We have to take this pattern and invert it, make an exact copy of it except inverted to the origin and make the measurements again. And this allows us to eliminate any kind of errors introduced by artifacts within the science instruments themselves, any kind of field distortion. And so that all worked very, very well. We found out we had to move the secondary mirror quite a bit. It was even further than we had to move it before in global alignment, but more surprisingly, we needed to tilt the thing by more than half a milliradian. And that was a large motion. We were not expecting it, but nonetheless, this is what it's designed to measure. So we tilted that and repeated all these measurements and then found that we had essentially no errors left to correct. So the process worked beautifully. At this point now, basically everything is aligned up except for the images have to be stacked and phased again, but all the field dependent errors are taken care of. All right. So then what we did is we went on to repeat this global alignment process. We moved the spots out into this big array again, and we used the secondary mirror to defocus the telescope. And this time we're going to correct everything that is left. We're not going to move the secondary mirror anymore, but we're going to move things like this. We're going to clock the primary mirror segments and translate them. And after just a couple of iterations, we ended up with everything corrected to the extent that it could be corrected, 44 nanometers root mean square. And all we have to do now is complete the fine phasing of the segments and things would be perfect. Here's a comparison of that wavefront we got in space with the ground measurements. And I say make ground measurements, but that's kind of a misnomer because it was never really measured on the ground. And that's what's fascinating. This was, because of the presence of gravity, all of these figure measurements have to be inferred from multiple measurements where you rotate it and you combine them and you do all kinds of backouts and everything. So the fact that we could get something that so perfectly represents what we were trying to build is just amazing. And the space-based measurement is noisier because it's from phase retrieval and not an interferometer, but I hope you can see my mouse. But if you look up here, there's a couple of places where you see differences. For example, you see a little dot here that does not appear in the ground counterpart. And there's also a little smear right here in this segment that does not appear in the ground counterpart. Those are the first known micrometeor impacts, but you can clearly see them, but you can also see that they are not large compared to other artifacts that are already in the mirror. So they're fairly comparable to the polishing errors that are in the mirrors anyway, but they are noticeable. So then after correcting all those errors, we have to now tilt the segments so that they fall exactly on that crosshair. Now, you can't make a mistake, because if you make a mistake, you've effectively tilted the primary mirror, and you don't want to do that. So these spots have to go exactly onto those crosshairs, exactly onto them. And well, as you can see, what happened is they didn't. I went to bed, but it's no problem. They got just make a measurement, and we moved them again and put them in the right place. So in this case, since most of the piston errors are now fixed, we can stack these images, but using this phase retrieval that we talked about. This is the weak lenses. We can take 6 different defocus positions using these weak lenses. And we started off by getting most of the tip and tilt corrected on 17, and then brought in the 18th segment that we were guiding on, and then got the tip and tilt corrected on that. Now here's an example. You can see this was the one on the left here. This is how it was stacked earlier using centroids only. And here it is stacked using the phase retrieval after correcting most of the piston errors. The light is now well within the coherence length of the filter that we're using, or the errors are, so you get all this interference that you wouldn't see otherwise. And we're going to do the coarse phasing a couple more times. And here we are. In this case, I took the spectra that were extracted and scrunched them up left and right, so you could see the barber pole patterns on there a little clearer. All right, so after correcting the final little piston errors, we did the fine phasing operation one more time. And now not just correcting tip and tilt, but also the last little, nanometer level piston errors between the segments as well. And we started off with 166 nanometers, and after a couple iterations applying all the corrections, we got 46 nanometers root mean square, and the telescope is now perfectly phased, at least at the single field point. And here it is. This was the very first image we took. We intentionally saturated the star because we wanted to see all the galaxies in the background. And this is neat. This first image that we took down had 241 galaxies in it. Unbelievable. One of these galaxies even had a supernova. You take your image, why not have a supernova? What the heck? So if you went back and looked at that again, it probably wouldn't be there. But just amazing. One of the colleagues at Space Telescope, Matt Lalo, took this and extracted all the galaxies from that image and organized them according to their type. And we made a nice little poster out of that. So how do you celebrate the very first image, finally getting this telescope phased? Well, this is James Webb, and he's the person that the telescope was named after. He really was a remarkable individual. We would never have gone to the moon if he wasn't the administrator of NASA during that time. He was born in 1906. Well, this bottle of cognac was also born in 1906. And I am proud to say that my good friend Anthony Gallier and I were the owners of the said bottle. And we opened up that bottle. The director of Aura, Matt Mountain, got some special glasses, and we raised that glass and we toasted James Webb and the telescope that bore his name. I have to tell you, I don't actually drink alcohol, but I made an exception in this case. And I didn't just have one, I had about 4 glasses of that, and it was amazing. I got pretty tipsy, which is a grown-up way of saying drunk. And I remember when I got back to my apartment, I had an apartment within walking distance of the Institute there. I tweeted to a friend, I said, I wish you could see the universe from my perspective. Just searching for the words that come so easily when you've had alcohol. And I said, we are surrounded by a symphony of creation. There are galaxies everywhere. And later, NASA asked me for a quote, and I said, well, I don't know what to say. What am I supposed to say? But I remember that tweet, so I copied and pasted and sent it to them, and they printed it and it went viral. It was in Forbes magazine, it was on CNN and everything, and somehow people just liked that idea, a symphony of creation. But they didn't know that I only said that because I was toasted on pre-prohibition alcohol at the time. So now you know the story. Yeah, so there it is. I'm only one of a few people I know that have ever been drunk on alcohol from before the prohibition. but that was quite a party. It was quite a celebration. I'm very glad we did it. And in a few years, I'll have actually finished paying off the bottle. So this is what the stars look like while we were stacked but not phased. And then here is what they look like after being phased. Slightly different field position, but you can see they're much crisper now. Now they're diffraction limited. Now on to New Zealand. I was going to bike across Australia, but it was just too hot. I mean, the kangaroos were dying. So I went to New Zealand instead and biked the length of both islands. What a beautiful, wonderful place. Man, I got to tell you, it was a hard place to be. Very difficult roads and stuff. Particularly, they're what they call bicycle routes. It took me a while to figure this out, but a bicycle route really means mountain bike trail. And I decided that I wanted to do these, even though I had a road bike. And so I went up this trail. This is a single track thing, went through the mountains. It went for quite a ways. At one point, I had to ford a stream. And I'm in the middle of nowhere at the top of this mountain, and I see a pair of cyclists coming towards me, and their bikes looked like mine. And I was so happy because that meant the rest of the trail was probably navigable if they are there. But I told them, I says, hi, I got to tell you, I'm really pleased that your bicycles look like mine, because that's a good sign for me. And they looked at me, they didn't say a word. And then finally they said, you must be Dr. Acton. And I can't believe this. You're in the middle of mountains and you run into some strangers and they seem to know who you are. Well, that's just New Zealand, right? I had given a radio interview a couple weeks earlier or something like that, or maybe even a week earlier. And everyone in the island, everyone in the country heard it. And so they knew I was there, what I was doing, the bike ride and everything. So anyhow, that was it. Some of the roads were pretty tough, but I love the diversity of the landscape. I would love to go back to New Zealand. There I am in Baldwin Street in Dunedin, the steepest street in the world, supposedly. And then I woke up one morning and this was on the front page of the newspaper. This is, they'd snapped my picture and made this graphic and everything. And I just could not believe it. It was quite an honor. In any case, we're getting close to having the telescope phased because we have one more thing to do, and that's to go around and look and try to retrieve the phase from all the various science instruments. Now this gets harder because on NIRCam, we have small pixels, the images are well sampled, and the filters are narrow band, but in the other instruments, that's not the case. Now here's some examples of how the Fine Guider and NIRIS and MIRI will look, or how these are those images when I've taken the secondary mirror slightly out of focus. And here shows an example of why this is such a challenge. It complicates the phase retrieval, but it's manageable. We can still do it. And here's what we got. I don't show the results for near spec, the spectrograph, but we had those as well here. But basically, no matter what we did, we weren't going to make the wavefront any better. And so all we did was just a slight balancing of the focus turns, and that was it. The wavefront sensing and control process was completed. So the last thing we did was something known as a thermal stability measurement, where we pointed the telescope to one part of the sky and just watched to see how the telescope, the wavefront would change, how the alignment would change over time. It turns out it was actually quite stable. But somebody had this idea. They said, all right, sure. So you're able to show that the telescope pointing is stable. How do you know the pointing is any good? Because even though you're locking onto a star with your fine guidance sensor, how do you know that the telescope isn't rolling about that lock point? And so we said, well, okay, we'll use the primary, the first guider, the primary channel to control the pointing, but we'll use the redundant guider to take like these 20-minute exposures. And if there's any smearing, any rolling of the telescope during that time, we'll see it in the images. Well, there wasn't any. Now you got to understand, a 6.5 meter telescope in deep space with no competing light sources, 50 degrees Kelvin, and you've got a science instrument that's not really a science instrument, it's just a detector. It's sensitive from 1 to 5 microns with no filters. If you take a 20-minute integration of the sky like that, it's just going to be unbelievably deep. Imagine what happens if you take 100 of those images and average them together, and that's what this represents. This is by far the deepest image of the sky ever taken by anyone. It's much deeper than the Hubble Ultra Deep Field. It's just incredible. I sent this image out to an astronomer at UCLA, James Larkin, a galactic astronomer, and he said he estimated that this image contained 15,000 galaxies. For example, you zoom in, every one of those little dots is a galaxy. There is no dark sky. Dark sky is a myth. If you look deep enough, there's galaxies everywhere. So with that image, that completed the process of aligning the telescope. It also completed my ride, the various places through the world. And I always like to give credit where credit is due. Here's some of the people that have worked on this. And that's it. Guys, thank you so much for your time. I'll turn it back over to Ed now.
Well, Scott, this exceeded my expectations. Just a very dramatic, fantastic adventure you had, not only riding around the world, but making this fantastic telescope work.
Quite an opportunity.
Fantastic. And you're now, I hope, Bruce, are you seeing my cover sheet?
I'm seeing it.
Okay, so I got a few minutes here. Now, Scott gave me a fantastic handoff because he was talking about the galaxies that were seen in these deep field images produced by James Webb. And what I thought I'd do is take about 10 minutes to explain the science that can be extracted from those deep field images. First thing I'd like to show is here's kind of a history of how far back in the history of the universe various kinds of telescopes can reach. So 30 years ago, ground-based telescopes could reach back to a time, say, 1 billion years ago. And then Hubble was launched, of course, in 1990 and repaired in 1993. And we could see back 4 billion years, that's the Z values, 5 billion years and so forth. And then Hubble did deep fields, actually a couple of them, but here's James Webb, designed to see back just 200 million years after the universe was born in the Big Bang. And one of the key things that astronomers measure is the cosmological redshift that occurs because the universe is expanding. So if we look at a spectrum of a relatively nearby galaxy, and compare the spectra here, we're looking at hydrogen and oxygen. If you go in a laboratory here on Earth and measure that spectrum and then compare it to what you see in a distant galaxy with a redshift of 0.087, you see that same spectrum, but it's shifted because the galaxy in question is moving away from us, propelled by the expansion of the universe. If you look at an even deeper, a more distant galaxy with a different Z value, you see the same spectrum, but shifted all on this scale here. So what astronomers have done is assigned this shift, given it a name of Z, and what we see is a relationship between the Z value and the size of the universe when the light from this galaxy was first born. So if you have a Z of 0.087, add that to the number 1, so you have 1.087, and the universe is that much bigger now than it was when the light from this galaxy was first emitted. Now here's one of the famous pictures produced by James Webb, probably released in June of this year, and you see the spectrum of this galaxy, this little dot, from light emitted 11.3 billion years ago, and here's hydrogen, oxygen, and so forth. And here's a different spectrum from this little dot, which is actually a galaxy with 100 billion or a trillion stars, and the same spectrum is present, oxygen and hydrogen, but it's shifted. Now, what NASA has not done for the public, I'm going to do for you now, and that is to show you what information is implied by the age of the light coming from the 4 different galaxies highlighted in this deep field image. And you see they range from 11.3 billion years of light travel to 13.1 billion years of light travel. And I'm going to show you that from this information, how old that light is, we get the value, the redshift, the cosmological redshift, and that tells us how far it is right now to that galaxy, if it still exists, and the relative velocity between the Milky Way that we live in and the galaxy that appears in the image right there. And in this case, this item right here, this galaxy, which is a primitive early galaxy, if it still exists, it's receding from us at 50% more than the speed of light. And that does not violate Einstein's theory. This is not motion of this galaxy in the space in which it's embedded. Rather, it's motion of the galaxy because the space between the Milky Way and this galaxy they're being carried apart by expansion of the universe, propelled by dark energy, something we don't have time to talk about tonight. So you'll see in these images, here's the next one, this galaxy has a higher redshift. It's much farther away, 28.4 billion light years, and it's going away from us at twice the speed of light. And here's another one, 2.3 times the speed of light. And this one is the oldest of the galaxies, the most primitive. And that galaxy is now 34.4 billion light years from us and moving away from us at 2.5 times the speed of light. Now, this frequently is handled incorrectly in the press. If you tell, I've seen this over and over. Actually, I have an example that I'll show you in a second. So you got to watch out when you read informal articles in the press. But here's the way this works. If you know the Z value, the redshift of a galaxy, you can immediately use this curve to find out when the light was emitted. And you can draw a little line like this. So if you know the light was emitted 11.3 billion years ago, you can go over and down. That gives you a Z of about 3.1. And with a Z of 3.1, here's Z of 3.1, we can go up to this curve, which is called the look back distance. And we can go over to this scale, and we see that galaxy is now 21 billion light years away. But here's even a prestigious journal like Scientific American gets this wrong. This article says astronomers have spotted the most distant galaxy 13.5 billion light years from Earth. That is wrong. The object started producing light that Scott's telescope can detect now, and that light has been traveling for 13.5 billion years, but it's not 13.5 billion light years away, because while that light's been traveling, the universe has been getting bigger. And in fact, hang on, that's wrong. The actual distance from Earth or the telescope to this distant ancient galaxy is actually over 33 billion light years. So be careful what you read, and I'm embarrassed to say that Scientific American got that wrong. Now, are we doing the right stuff? Are we getting the right answers? Here's a group of measurements of galaxies using a different kind of measurement technology called acoustic oscillations. Each of these dots represents the position and redshift of an individual galaxy with error bars. And we can now model this using Einstein's theory of relativity. And this green curve uses the best measurements we have for the amount of matter and dark energy in the universe. And you can see the agreement between Einstein's theory and these positions that are observed with telescopes like Scott's. So we have a self-consistent view of the universe. There's much more to the story that we don't have time to go into now, but I just wanted to show you that progress, serious, amazing progress has been made. And now James Webb is going to give us even more information about the oldest, highest redshift galaxies. And that will add to our ability to characterize the universe and make predictions about its future. Now, one last technical detail here. This blue curve shows the speed of recession of galaxies as a function of redshift. And you can see it's just normal business for astrophysicists to find objects receding from us that at far greater than the speed of light because of expansion of the universe. Okay, I think that's all I want to say. So once again, thanks to Scott for the fantastic travelogue and story. I don't want to abuse our time together. Oh, let me just do this. This is my own animation of a comparison between Hubble images, which are indicative because they have the two diffraction spikes here crossed, having to do with the design of the telescope structure. And now we push the button. And if I'll do this a couple of times, and this is what James Webb can see. So let me go back. Look in this region here. Remember that Webb and Hubble do not look at the same wavelengths. But just take a look and pick one of these ellipses. This is what Hubble could see in a deep field image. And now let's switch to James Webb. And you can see in every case, like this ellipse here had maybe 6 or 8 little dots that Hubble saw, and James Webb sees 15 or 20. So this just complements what Scott was saying about the ability of the new telescope to see deep into the early universe and see these ancient galaxies. And I think, yeah, that's the end of my presentation. Okay, thanks for listening to me. And once again, congratulations to Scott on his adventures and surviving his heart issue. I remember very well when his heart problem emerged, and I was hoping to start getting messages from him traveling around the world. And instead, I kept getting messages from a hospital in Longmont, I think. So thanks again, Scott.
Yeah, you're welcome. That's great, Ed. Thanks a million.
Okay. So Bruce?
Yeah, wow. This is just an amazing presentation. I'm sort of embarrassed I didn't know more about who Scott was. Just thought he was Ed's sidekick, but now I realize he's on a par. So
Yes, I just let me make a comment about, Scott just talked to us for 45 minutes about the methodology they use to get from a $10 billion worth of hardware and software and make it work. To me, this is like watching a great athlete who makes it look easy to hit a baseball or hit a golf ball or do those things that we marvel at. And that's what Scott has done. He's made it look easy, and it's not. It's a super complicated thing that involved thousands of people, but he's at the tip of the spear, because without the alignment of the telescope, we don't get images like this.
yeah, I mean, I've spent time aligning in production mirrors, that are, off-axis mirrors like this that are, 10 inches in diameter. So getting all those different pieces to line, and oh my God. It only took, how long did it take? Well, but let me open it. Let's open it to questions.
Yeah, go ahead.
How long did it take? Was it just a couple of months before it was aligned?
Well, we launched on Christmas Eve.
Yep.
And basically handed the keys to this telescope over to the Space Telescope Science Institute, like on the end of April, May 1st. So, solidly 4 months. But, that's 4 months with basically 3 shifts a day, working on it.
And that didn't clog your arteries back up?
Well, I'll tell you, I went into this process of vegan and I came out with a slice of bacon in each hand. It was the hardest thing I've ever done. It was unbelievably
Yeah.
stressful.
Yeah.
Could you get out of screen share, please? So we could see everyone.
Sure.
Still screen share. Thank you.
Yep. And one other question I have for you, because having spent a lot of time putting images on detectors, what's the size of the detector, and then what's the size of the array that you're dealing with?
Well, I mean, the physical size, it's in terms of
Yeah.
centimeters or so.
Yeah.
Yeah, I think they're like, 4 inches square or something like that.
But I mean, the individual detectors, how many microns is it?
I believe each pixel is, 30 microns on NIRCam. I think that's it.
Okay.
2,000 of those, 2,048. But then there's 4 of those into a NIRCam module. So 4,096 by 4,096.
Okay.
I have a question. When it gets translated into the visible wavelengths for us to look at, is there any correlation between, the infrared wavelengths, and red is hotter and blue is
Yeah,
cooler?
they ultimately make it up, right? But I mean, they there's kind of a standard. The longer wavelengths are red and the shorter wavelengths are blue. But that might be
Would
microns.
red be farther away or younger?
Well, it's certainly redder. I mean, the galaxies are, if they're brighter in the red, they're further away usually.
That means they're younger and they're hotter.
Well, the younger, I mean, I don't know if how the temperature works out, because I'm not an astronomer in that sense, but yeah, I mean, that's kind of one of the interesting results so far, right? Is the young galaxies look just like our galaxies. Like those ancient galaxies that have been, like the one in the Scientific American got wrong, it's 200 million years old, and you can see oxygen and neon in it. Those are things that that stars have to be born and die and go supernova in order to create those. So they're very similar to our galaxies that we see closer to us. It's kind of a mystery.
Yeah, it seems, I'll maybe throw something in here. It seems like the chemistry of the very early galaxies and the processes that went on just a few 100 million years after the Big Bang, very similar to the galaxies that are near us and are much, much newer. So that's a field of active research, is how is that possible when you have these processes that are using the very first stars in the universe to form galaxies, seem to have been doing the same thing that's going on now, 13 billion years later.
Yeah, isn't that something? Yep.
Yeah, that should be,
That's an enigma.
yeah.
So in layman's terms, just, you're looking at a speck out there, right? And you're able to determine how far away it is, right? Or how far away it was when the light was emitted. How do you take each of those specks and decide how old it is or how far it is?
You have to use a spectrograph, right?
Okay.
Part of the
Yeah. Yeah, so the answer is each of those galaxies, each of those dots on the sky has its own redshift. And by parsing the light, not only do you get the redshift, which tells us the distance and the speed at which it's moving away from us, but we also get the chemical composition of the galaxies. And in fact, if I can indulge me, I'm going to go back to my presentation for just a second and point out that, where is it? Okay, I'm losing it. Yeah, you see each of these structures here. There's some central object here, a collection of galaxies that's distorted the light from a distant object, an even more distant object. And this light from right there And this light from right there and there and there, if you analyze the spectrum and the redshift, you find these are all from the same light source. It's hidden behind this bright object, which is a cluster of galaxies. But the chemical composition and the redshift are the same. This is distortion caused by gravitational bending of the light rays as they propagate from a distant galaxy to us. And these are parts of what are called Einstein rings. And we know they're from the same object because, as I say, the chemical composition of that distant galaxy and the redshift are the same. So what we're seeing here in this image is distortions produced by this supermassive collection of matter included within are black holes and just enormous amounts of matter distorted the path of these light rays.
Okay, thank you. Any other questions? We'll open it up. If you do have a question, unmute yourself when you ask it.
I've got a question. So looking at this panel here, Ed, you start at 11.3 billion and go to 13.1 billion. It looks like you've compressed everything over 2 billion years, starting 11 billion years ago. What happened before 11.3 billion? It's just 1.5 C. Is it just a gradient from C to 1.5, from 0 to 1.3 billion years?
All right, so let me clarify. This is the light travel time. So
Right.
this is the oldest galaxy in the image that was highlighted. There may be older galaxies in this image, but just for the public consumption, NASA highlighted these 4. And when you get back here, you're looking at the oldest galaxies, among the oldest galaxies that have ever been detected. 13.5 right now is the oldest galaxy that we've ever seen. And we have seen a few stars that are slightly older than that, coming from the very early days of the universe when there weren't enough stars to form galaxies. So I don't know if I've answered your question, but this is newer than this. This is older.
No, what I'm asking, where are all the galaxies between 0 and 11 billion years?
Well,
age?
okay. So remember that Webb is an infrared telescope. So the newer galaxies that have hydrogen and oxygen and other chemicals, they don't appear in the Webb image because it concentrates on infrared reaching into regimes where we see older galaxies. The newer galaxies, we would have to be using Hubble's images, which are in the visible spectrum and the very near infrared.
Okay.
So
All
this
right.
Webb is designed to be biased towards the longest wavelengths. I think I have that's in this, whoops, it's right here. Webb is designed to be really effective out here, the oldest galaxies with the largest redshifts, and that will be seen in the deep infrared. Hubble is working at much more like visible wavelengths and doesn't reach very far into the infrared. Scott might have additional thoughts on this.
Yeah, I mean, I think, the real close ones, they weren't pointed at anyway, right? I don't know
Right.
what the age of some of those more pronounced galaxies are in that picture. But, some of them you can see the little spiral structures in the arms, those aren't 13 billion light years away.
Oh, right. Yeah. Some of these have a more, what you might call a more modern, like this one right here.
Yeah, you look around, you can find several that are classic Star Trek-y appearance,
Right.
Okay.
Those are just selected out of the picture.
Yeah, right.
Maybe we can
So
ask
there's
a
not much-
bicycle question.
Sure.
I have a quick question. I'm curious to know ultimately how much and how far will we go with the Webb? How close are we going to get to that big moment of the, when everything started?
Yeah, 200 million years.
Right here, Judy.
That's it. So what's beyond that,
Well,
the thing?
but prior to this, there were no
Yeah.
stars, and the astronomers call this the dark ages.
Right, the dark, right. Okay, so
And-
we're at the edge.
Well, let's clarify. There were stars here. There was the dark period where there were not stars, but way
Right.
back over here, which Webb
Right.
cannot see, is the cosmic microwave background.
Correct. Okay.
That's the highly redshifted leftover radiation from the Big Bang.
The
And,
band.
and Webb is not designed to see that. We already have the Planck telescope and
WMF and Kobe.
Kobe. There have been 3 major spacecraft that look at the cosmic microwave background. But between
That's right.
So between the microwave background and this point, there's nothing to see. This drawing is a little misleading because it shows light sources. The universe
Right.
was dark. There just weren't any stars.
So what is the next step on analyzing these images? Are you just cataloging everything and then just saying this is how old it is and this is how far away it is or was?
Well, yeah. So Scott, do you have a thought on that?
Well, I mean, you know, there are many different investigative lines that people are pursuing, and pushing this curve out is just one thing that Webb is doing. So I would imagine, over the next year or two, you should see something.
Right. This is data using what's called baryon acoustic oscillations. It's measuring positions of galaxies. And you see we're at a redshift of 3. Webb is designed to see back to a redshift of, let's get there.
33, no, 20. 20.
Right. Yeah, somewhere in here, 20. The microwave background is at a redshift of 1100 to give you a sense of what goes on. So, but Webb is unique because it's out in space, it's gigantic, it's got the right instrumentation, it's designed to function out here and see the first stars, but it also has a big mission to find extrasolar planets. So one of its scientific products is going to be expanding the catalog of planets in other solar systems.
I have a question. Can you hear me?
Yes.
The process you described of identifying each of the 18 mirrors, which is something I hadn't even thought about before. So you had to move the mirror and see which image moved, and that allowed you to identify the mirror. How long did that process take for the 18?
That part took a couple of days. We had a leg up on it by moving to secondary, and so we had identified 12 of them. But then to confirm those, and so because it's image move image, and then you move every segment, and so maybe you find 4 or 5, and then you got to go back and do that again at a different part of the sky with you moving the ones that you haven't found yet. So it took I'm guessing maybe not quite 2 days to do that.
Okay, well, I imagined much longer time.
Well,
Thank
one
you.
thing the thing to keep in mind is in those pictures that I showed, anytime you see a little spot move, somebody on the ground and on the team had to decide that we needed to move a segment And the software had to produce commands to move that segment, and that had to be turned into low-level commands that the spacecraft understands, and that had to be passed throughout the entire ground system. And it's actually, there's you might not realize it, but there's quite a bureaucracy involved in there that has to be gone through just to prevent some crazy thing from happening. And and then it has to go up, down through the deep space network, wherever in the world happens to be pointed at that telescope. And the commands to the spacecraft, and then all that things has to execute, and that takes several hours, and it all has to come back down and then be processed through the deep space network, and eventually go through the ground system and everything. And then eventually it shows up on our computer, and we can look at it and decide, what to do next. But it's so easy to show those little animations. This thing moves, and take an image, and this thing moves. But that's what it took 4 months, so.
Thank you.
Sure, yeah.
Question. If the universe is expanding such that stars are separated from us by 1.5 times the speed of light, does that mean that eventually the light that's being emitted today from those stars will never reach us?
Yeah, the universe is getting more dilute. Objects are moving away from each other. And when I talk to young people about this kind of thing, I point out that this is a good time to study astrophysics, because in the far future, the only stars that a future scientist will see will be the stars in the Milky Way and the little satellite galaxies and Andromeda, which is the galaxy that's going to collide with the Milky Way. They will have no mechanism for figuring out that there was a Big Bang, that there are hundreds of billions of galaxies that are out there, but the light from those galaxies will never appear here because the expansion rate of the universe exceeds the speed of light. And so if you want to study the universe now and build a model of how it functions and how it'll evolve, this is a good time to do it, because 20 or 30 or 50 billion years from now, only the local stars will be seen. The rest of the sky will be dark.
I'll be darned. Huh.
Thank you.
Okay.
Well, I guess maybe we should wrap it up if there aren't any more pressing questions. We're going to have another science for the board in a month, but I think we just need to relish this one. I'm going to put everybody on here, and I'd like to get all the remaining folks to give a applaud. This was a great.
I'm clapping for Scott.
Yeah.
Thanks very much.
Thank you so much.
Well, I'm clapping for both of you.
Yep.
Thanks so much. That was.
You're
that was
welcome to join us
fun.
anytime, Scott. You're on our list. You're going to Raipu will be talking next month, and he is a world-renowned expert in energy. In the idea that we don't have enough energy to go around. So.
Well, I'll do that. I'll look for those emails.
Okay. Thank you.
Hey, Rainer.
Thank you, everyone.
Hey, how you doing, Scott?
Bye, everybody.
Bye.
Bye.
Hi, thank you very much.
Hey,
That was
thanks,
awesome.
Thank you.
It was-
You're welcome.
it was
Very
fantastic.
interesting.